Hello everyone. So welcome to the presentation here. So today my name is Sagar and I'll be talking about the structure of atom, their energy levels, band gap, and let us say based on band gap how the classification is made into conductors, insulators, and semiconductors. The first thing, these are the topics which we are going to study today. Structure of atoms. So basically this course will not include any kind of prerequisite, so everything will be taught from very basic, from the structure of atom, from electrons, protons, neutrons, their distribution in an atom, then the distribution of atoms in a conductor or any material, and then let us go deep into semiconductors. So we will begin the topic with the structure of atom here. Okay, let us consider only this. So as we know, the center of the atom is nucleus, which is comprising of protons and neutrons, and that is positively charged. And electrons will be revolving around the nucleus in a definite orbit. So they possess their own energy and they will be revolving around the nucleus. So number of electrons is called atomic number, and that's it. So I hope you know this, and we will get deep into the structure of atom later on. So for now, we need to know that the center of the atom is nucleus, which is positively charged, and around it there are many orbits at different energy levels, and it has electrons revolving in it. So let us just consider one atom, the dawn of semiconductor. So silicon atomic number is 14. So we'll just write the configuration, electronic configuration, that is 1s2, 2s2, 2p6, 3s2, and 3p2. So you can see here that okay, you can see that first orbit is completely filled, second orbit is completely filled, 2s and 2p, but the last orbit is incomplete, so it has only 4 electrons, right? It requires additional 4 to complete p orbital, and that is 3d, so this is incomplete. So in any kind of material, the inner orbits which are completely filled, which are stable, do not take part in any kind of any kind of properties like in electric current or magnetic field or something like that. Some many properties. So mostly, most commonly, only the outside orbits which are incomplete will participate in bond formation, and they participate in electric current or any other features. Okay, so now we need to know that, so this is first orbit, this is second orbit, and this is third orbit. Okay, so first orbit, second orbit will be at a greater radius, third orbit will be at much greater radius. Now the energy of the electrons of higher orbits is higher than lower orbits. Now the question is why. So as I told, the electrons in third orbit has higher energy than electrons at second orbit. Electrons at second orbit has much higher energy in the first orbit. Now the question is why. So as we know that nucleus is positively charged and electrons are revolving around the nucleus, uh, the Coulombic force of attraction, okay, so I'll just write it down. The Coulombic force is inversely proportional to square of distance. As we know, so Coulombic force is inversely proportional to square of distance. So in the first orbit electrons are much closer to nucleus. That means they have the distance is very less, and that's why the Coulombic force of attraction is very high, and hence they do not possess much higher energy. They are very attracted to the nucleus. But outer electrons are much free than inner orbit electrons, and they possess much more energy than inner orbit electrons. So as we know that only the last orbits, valence orbits, valence electrons participate in bond formation or any kind of properties like electric current. And also we know that the higher the orbit, greater is the energy of electrons, and they are much free than inner orbits. So this is what we should know. And let us get now into a material. Now, as we discussed a single atom, now if you consider a crystal, okay, a crystal, crystal means every semiconductor it will be in the form of crystalline in nature, okay. So that is why, and crystalline most of the times crystalline materials have a cubic lattice structure. That means they're very periodic in nature, okay. Periodic in the sense the atoms will be placed at equal distances from all nearby atoms. So it's period. It's just like a cube. So it's a cube. Okay, and we know that a cube has a single property, that is the edge length. Distance between two nodes is going to be the same, right? So that is one important thing we have to know. So we have only one thing parameter called a distance between two atoms. The structure of atom inside a crystalline material is periodic. Okay, so we studied about one single atom, right? So if you consider a crystal, there will be millions and millions of atoms separated by some distance with the nearby atom. So there will be atoms all around. So in a 3D view, but I have represented only in the 2D view. So these are the two atoms separated by a distance. Okay. Now, as I told, they have, we will consider only two energy levels as they only participate in this kind of interactions or any electric current and all that. So there is 3s and 3p. 3p has greater energy level and 3s. So 3p is mentioned above and 3s is below. Now what happens when in a material when two atoms are nearby? Okay, so when a single atom, isolated atom is present, it has this kind of energy states. Okay, it is a unique energy states 2p, and there is 3s and there is 3p, and you can mention it here. You can draw the horizontal lines and show the energy. But what happens when many atoms come closer? Okay, so when many atoms come closer, that means the distance is going to decrease. Okay, I have written x-axis as distance and y-axis as energy. Okay, energy is mentioned 3s and 3p. Now when two atoms come closer and closer, okay, at a certain point their energy level, these are the energy levels, right, 3s and 3p, are going to discretize. Okay, I will explain you that what is it. So distance is the distance between two atoms in a crystal. Now, when you decrease, that means you're moving towards the origin. You're going to decrease the distance, and when you decrease the distance at a certain point, their energy levels are going to uh, discretize. That means your every energy level is going to split up into two. See, it is going to split up. Okay, so every energy level is going to split up like this. Okay, so 3s. We do not mention the lower energy levels because they do not participate. Okay, so these are going to split up. Okay, so this is called discretizing. So what happens is when you bring two atoms closer, at certain point their energy levels are going to discretize. They are going to split up. So there are many energy levels here and here. Okay, so no energy levels here. So they're going to split up. Mhm. Now what happens at equilibrium distance? Okay, now okay, so before equilibrium distance, so this will continue. Okay, this will continue go on. Okay, and at some further, when you move much closer, when you bring these two atoms much closer, their energy states are going to further discretize. Okay, the energy levels, sorry, not there. So their energy levels are going to further discretize. Okay, it's going to be like this. Okay, so this is going to continue. So there are all energy levels here. Okay, there are plenty of energy levels here. So they are very, they have a very proper what do we say, the trajectory, but I'm not drawing it. So these are all filled with energy levels. These are all filled with energy levels. Okay, but there are no energy levels here in between. You see, these are going to split up here, and then here again they are going to split up. So there are energy levels here or everywhere here, but here there are no energy levels. Here there are no energy levels. They are going to split up like this. Okay, now this is equilibrium distance. What equilibrium distance means is that uh, if you take a crystalline material, if you take semiconductor from Earth's crust, without applying any kind of pressure, or without heating it, or without passing any electric current, if it is at room temperature, the material is at room temperature, the distance between the atoms and that material is called equilibrium distance. Okay, so I hope you understand it. So you have you take a material, a silicon material, and without, it's at equilibrium at room temperature, the air pressure, and you haven't supplied any kind of electric current through it or any kind of magnetic field. It's in a room temperature free, and that crystal will have a specific distance between two atoms, that is called equilibrium distance. Okay, now if you see at equilibrium distance, okay, I will just so I hope you understood this. There is 3p and 3s, and it is going to split up, discretize, and then it will again split up here, and this is where no energy levels, and this is all full of energy levels. Now at equilibrium distance, I'll just pull a straight line here. Okay, so this is at equilibrium distance. Okay, now I will just draw another xy axis. Okay, so it's the same. This is the distance, and this is energy. This is distance, and this is energy. Okay, now only at equilibrium distance, I'll consider only at equilibrium distance, and I'll just, you see here, this point is so there are energy levels from here to here, right, here to here, and there is empty, there are no energy states here, and then again it starts from here, there are full of energy states here, right? So I will just draw it using the same thing, in the same analogy. So this is a horizontal line representing this point, this all the energy levels here, and one more line here. Okay, so this line represents this point, all the energy levels in this region, and you can see below that there are a lot of energy levels, and above this there are many energy levels, but here there are no energy levels, right, in between. So I'll just, there are many energy levels here, so there are many energy levels here and also here. Sorry. Okay, so you can see that at equilibrium distance you have all the energy levels from here to here, and there is no energy levels here, and from here to here there are many energy levels. Now these set of levels, energy levels, are called is called conduction band. What is band? Band means there are many energy levels which all together we call it as a band. Okay, so I'll just draw a box here. So I will put all these energy levels in this box. Okay, and here I will put it all in this. Okay, okay. Now this is called conduction band. Okay, this is called conduction band, and this is called valence band. And this region where there are no energy levels, see, there are no energy levels. When I tell no energy levels, means that means electrons do not occupy any of this place, because there are no energy levels, electrons cannot occupy this level, this space. So since, see, you can say energy levels are not present here, that means here it's called forbidden energy gap. Okay, that means forbidden means electrons cannot be present in this level, so this is called forbidden energy gap. This is called conduction band. This is called valence band. Okay. Now We will when we further study these features, these properties, we will see that any kind of distortion in the material, like maybe lattice distortion or any kind of impurity you add, then there are some kind of trap energy levels formed here. Okay, so there are these are physical energy levels where electrons are present. However, in a pure material, a silicon or maybe anything, any material, this is called energy gap. These are forbidden energy gap. This is conduction band and this is valence band. Valence band is where electrons are present. Conduction band is a little bit far from valence band. There is energy gap. We will see whether these electrons can jump here and what is conduction band, why is it called conduction band, why it is called valence band, and based on these conduction band and valence band, how materials are classified into semiconductors, conductors, and insulators. We'll look into it, and we will further study a little bit deep and very clear from very basic. Okay, very clear what is current, what is voltage from the atomic perspective, and we will study semiconductors. And we'll specialize the semiconductors, okay, in semiconductors. So in the next coming presentation we will look into a little more deep into this. What are these energy levels? What are these energy levels? See, two electrons were at 3p, right, and two electrons were at 3s, and they were split up. These energy levels were split up, and again here they were split up. Now the electrons may be present anywhere in this because there are a lot of energy levels here. We'll see after this completion, after this division at equilibrium distance, where will electrons be present, and how it matters in deciding the parameters and features of a material. Okay, so thank you, and we will see in the next presentation.